Welcome to this explainer. Look, today we're going to untangle the AI hardware alphabet soup so you can finally stop bleeding money on the wrong chips. Right now, we're looking at a tech landscape that has just completely fractured. You've got inference costs absolutely spiraling, latency that's honestly pretty embarrassing during customer demos, and infrastructure teams sitting there wondering why their CPUs are maxed out at 80% capacity just handling basic networking. If you're sitting there thinking that simply buying a massive GPU cluster is going to magically solve all your problems, well, you're in for a massive shock. So here's our menu for today. We're going to set up a clear roadmap to help you navigate this incredibly fractured silicon landscape without getting lost in the acronyms. Starting off with what we're dealing with right now, the AI hardware crisis. We really need to expose the massive financial and performance costs of treating hardware as one giant monolith.
The crucial thing to understand is that just throwing cash at a massive GPU cluster, it's no longer a catch-all solution. The days of relying on a single universal processor are totally over. Today, the landscape is violently divided into 7 distinct architectural families: CPU, GPU, TPU, NPU, DPU, APU, and LPU. And each of these represents a fundamentally different philosophy about how silicon should actually spend its time. Using the wrong chip for the wrong job is exactly why a product that scales suddenly starts hemorrhaging money at inference time.
Now, the root of this entire crisis is something called the von Neumann bottleneck, sometimes known as the memory wall. Basically, processors can compute way faster than they can load data. To put that into perspective, in a standard neural network, a single 1024 by 1024 matrix multiplication involves roughly 2 billion arithmetic operations. The ratio of compute to data access is just astronomical. Every single architecture we're going to look at today was engineered to solve this exact problem in completely different, hyper-specialized ways. To really wrap our heads around these 7 distinct architectures, let's use an analogy. Let's step inside a bustling, high-end restaurant kitchen. Think about it like this. Your CPU is the head chef, coordinating the whole flow. The giant wok? That's your GPU, processing 12 pans simultaneously. Then you've got your rigid pastry specialists doing one precise thing perfectly. Those are your TPUs and LPUs. Your NPU is the catering team running super efficiently offsite. The DPU handles the mundane logistics so the chefs don't have to. And the APU is the chef's table, where prep and plating happen seamlessly on one surface. It instantly translates these complex acronyms into relatable jobs, and it proves a simple point. You would literally never put your head chef on the giant wok station. Taking a closer look at that head chef, your CPU, it's brilliant. It has a few deeply powerful cores built for latency and making complex decisions. When your code is a tokenizer or a pre-processing step littered with complex if statements, the CPU is completely unbeatable. But it fundamentally hits a wall when faced with massive parallel arithmetic. It just doesn't have the dedicated matrix multiplication hardware needed to handle the billions of operations inside modern neural networks. So let it orchestrate, but do not make it fry the food. All right, let's step over to the heavyweights. We're talking about the giant wok and the pastry specialist, where the massive, power-hungry AI training actually happens. Here's where the paradigm shifts entirely. While CPUs have a few deep cores optimized for low latency, GPUs flip this model on its head. They use thousands of much simpler cores built purely for raw throughput. They execute the exact same instruction across thousands of data points at the exact same time. This single instruction, multiple threads architecture is what makes them the absolute workhorse for AI. We are literally talking about up to 18,000 compute cores on modern high-end GPUs. 18,000! Combined with terabytes of high-bandwidth memory feeding those cores at lightning speed, the GPU is just embarrassingly parallel. It makes it the undeniable king of large-batch AI training. But there's a catch. GPUs rely heavily on dynamic scheduling, which brings us to a totally different approach. What happens if you take the hardware scheduler and just remove it entirely? Well, you get the Google Tensor Processing Unit, or TPU. Instead of a scheduler dynamically deciding which threads to run, a TPU uses a highly structured, incredibly rigid, systolic array paired directly with a compiler. It's a completely vertically integrated compute philosophy. It is not flexible like a GPU, but it is absolutely perfect for massive, dense transformer training. And the scale here is just mind-blowing. A single TPU physically pulses data through 65,536 multiply accumulate units in this rhythmic wave. Think of it like a heartbeat. The weights stay stationary in the processing elements, and the data just pulses right through them. It does the math without ever fetching intermediate results from memory. This slashes the memory bottleneck and energy consumption, giving you incredible performance per watt for that massive cloud-scale training. Okay, let's leave the heavyweights behind and move to the specialists. These are the unsung heroes handling precise inference, edge computing, and extreme system efficiency. First up, the Language Processing Unit, or LPU. How does it handle that memory wall we talked about? It literally just ditches external memory entirely. While a GPU stacks high-bandwidth memory next to the compute, an LPU puts everything directly into on-chip SRAM with massive internal bandwidth. Because there is no external memory fetching, there's no cache miss and zero scheduling spikes. It guarantees the instant deterministic speed you absolutely have to have for real-time voice agents. Moving over to infrastructure. Did you know that at cloud scale, up to a massive 30% of your CPU compute is wasted purely on networking, storage access, and security? 30%. It's an invisible tax on your system. That is, until you introduce the Data Processing Unit, the DPU. This is your logistics coordinator, sitting at the server edge, intercepting traffic and routing packets so your crazy expensive CPUs and GPUs can actually focus on generating model outputs. And when we look at power consumption for edge devices, it's a completely different ballgame. A data center GPU burns hundreds of watts. A server CPU, well over 100. But a neural processing unit, an NPU, it runs always-on AI features at single-digit watts. We're talking live transcription or voice wake words running constantly and completely saving their battery life while keeping the device snappy. Finally, rounding out our specialists, we have the APU. The Accelerated Processing Unit is our chef's table. It physically combines CPU and GPU memory onto a single chip. Because a pointer created on the CPU is perfectly valid on the GPU, data never has to be copied over a PCIe bus. This unified memory approach drops total memory footprints by up to 44%, which is an absolute game changer if you're trying to fine-tune large models on a single machine. So, how do we actually put all this together? Let's build an actionable, highly practical framework for your tech stack. Here is your playbook. The whole takeaway here is stop buying hardware in a vacuum and start matching the silicon directly to the workload. Doing massive training? Stick to GPUs for the CUDA ecosystem. Building real-time voice agents? You need the zero latency of an LPU. Running on a phone battery? NPUs are mandatory. Fine-tuning locally? Leverage the unified memory of an APU. And scaling a massive cluster? DPUs are simply non-optional if you want to eliminate that 30% infrastructure tax. I'll leave you with this final thought. True performance isn't found in a single magical piece of silicon. It's found in the orchestration of these specialized chips working together. So as you build out your AI stack, you really have to ask yourself, are you architecting a brilliant, highly coordinated kitchen, or are you just buying a massive wok and hoping for the best? Thanks for joining me on this explainer. See you next time.